Thank you very much, Cher, and good morning, everybody. My name is Khalid Chennoufi. I'm a PhD student at Mohammed 5 University in Rabat. Today, I'm going to present a paper titled Design and Implementation of a Robust MPPT Controller based on Artificial Neural Network and Backstepping Sliding Mode Controller. First, I will present the content of this presentation. I will start by presenting the objective of this research, and then I will present the proposed approach. This approach will be validated using both simulation and experimental studies. Of course, a conclusion at the end of this presentation. In order to maximize the amount of energy generated from solar cells, it is essential to use a maximum power point tracking algorithm, MPPT, which forces the PV module to operate at the maximum power point. Hence, the objective of this work is to propose an improved MPPT algorithm. The second objective is to prove the stability of the proposed method against the previous works. In addition, this work proposed an implementation of this algorithm in a CP converter using a low-cost materials. The proposed controller consists of a combination between artificial neural network and backstepping sliding mode controller. Unlike the previous works, which adopt single diode in the photovoltaic modeling and the traditional boost converter, the present work adopts double diode model for an accurate modeling, and in order to have a fast and stable tracking, the single-ended primary converter has been employed. The artificial neural network is designed to generate a reference voltage for each solar irradiation and temperature, which corresponds to the voltage at the maximum power points, while the backstepping slider mode is designed to track the generated reference voltage by adjusting the duty cycle of the CP converter, as shown in the figure below. The figure on top illustrates the current, the voltage, and the power generated by the photovoltaic panel. It can be seen from the figure A that the proposed method tracks the reference voltage perfectly within 14 milliseconds, while the other methods reach the desired voltage with oscillation after a while. In regard of current, which is shown in the figure B, the proposed method exhibits a smooth curve, while the other methods present shattering and overshoots. It's obvious that the proposed method tracks the maximum power points with high performance, while the other methods suffer from delay and fluctuations. The figure below illustrates the current, the voltage, and the power at the output of the converter. It can be seen from the figure that the voltage has been increased from 13 volt to 100 volts, while the current has been decreased from 8 ampere to 2.5 ampere, which make it suitable from some equipments that require a low current. However, the output power of the converter has been decreased from 245 watt to 231 watt, which represents only 5% of loss. In order to test the reliability of the proposed method in real outdoor conditions, an experimental photovoltaic system has been built as shown in the first figure. The proposed system consists of a 30-watt photovoltaic module, a resistive load, the proposed controller launched on Arduino board, and a CP converter connected with sensors. The proposed maximum power point tracking algorithm needs the employing of 7 sensors. However, the number of sensors has been reduced by using a sample equation instead of a radian sensor and a divided voltage instead of commercial voltage sensors. It can be seen from the figure A that the proposed method tracks successfully the reference voltage in 75 milliseconds. Thus, the module has been forced to work at its maximum power points. In addition, the figure B shows that the output voltage has been increased from 17 volts to 28 volts. In this case, the CP converter was configured to work as a boost converter, which is widely used in power conversion system applications. In this paper, a robust maximum power point tracking algorithm has been presented. The proposed controller has been carried out by combining slide mode and backstepping controllers in order to track the reference voltage generated by the artificial neural network. The double diode model has been adopted to ensure the real behavior of the photovoltaic parameters, and the single-ended primary converter has been employed in order to have a fast and stable response. The validation of the proposed method has been confirmed using both simulation and experimental results. On one hand, the simulation in Simulink software shows that the proposed controller exhibits his stability and rapidity against the previous works, and on the other hand, the experimental study shows that the proposed controller ensures the maximum power points in the outdoor condition successfully, and it can be easily implemented using low-cost materials.